What do you want to hear about? Julia, you.
I don't know, actually.
Have you looked at the list of topics?
I glanced over it. I've had like other finals that are due first, which is
Sure.
I've been focusing more on, but I can show it again.
Yeah, take a look, and it's this. If you don't have questions, that's okay. Anything anybody wants to hear about?
I was wondering if we could go over a problem
Yeah.
from the homework.
Yeah.
Problem 4 from chapter 3.
What? Let me take a
It has to do with showing, finding subsequential limits. Oh, the limb soup and the limb.
Okay. Let's take
The
a
upper
look.
and lower limits of a sequence. And I feel like I kind of got what was going on, but I don't know if I did it rigorously.
Yeah. Okay. Yeah, I'm not sure myself. So let's see. So you've got some sequence. S of n and S of 1 is 0. S of 2m plus 1. So the odd guys are you take the previous guy and you add on a half, right? And then the even guys are you take the odd guy, you take the previous guy, and you divide by 2, right?
Mm-hmm.
And it says find the upper and lower limits of the sequence, right? So, right, so for the odd guys, you take the previous guy and you add on a half. You take the previous guy and then you divide by 2, right? So you add on a half, right? 4, that's a half. And then you take the previous guy and divide by 2, and so on and so forth, right? So, so yeah, I don't know. Let's see. Yeah, I haven't thought about this one. So I mean, let's think.
Well, I was wondering if it's like appropriate to kind of define 2 subsequences of it and write out the odd guys and the even guys and kind of treat those as 2 subsequences and then show the criteria for the upper limit and lower limit respectively apply to those sequences, because if I think it was the odd.
Okay, sorry, just let me. I'm sorry. Give me
Yeah.
1 minute. So add a half, divide by 2. Add a half, right? Add a half, divide by 2. Right? Divide by 2. Add a half, divide by 2. Add a half, divide by 2, right? So you see there's a pattern going on here, right? Add a half, right? So this is actually pretty straightforward. Divide by 2, and et cetera, right? So every time you're adding on this, every time you add on a half, you're adding on sort of like the top term, right? Right. So you add on a half, you divide by 2, and that results in a power. That results in a power of 2. That results in a sequence 1/4, powers of 2, starting from 2 squared. And then when you add on a half, you add, and then it just extends. So this is pretty I think this is pretty straightforward as what's happening here, right? So right, so that right, so yeah, you see what's right. So as a picture, right? As a picture, right? What you're doing is, well, you start off at a half, right? You divide by 2, right? You divide by 2, and then then you add on a half to that, and then you divide by 2, right? And then you add on half to that. You divide by 2. You add on a half to that, and you divide by 2. You add on a half to that, and then you divide by 2, etc., right? And so you see what's happening. It's going to, the upper limit is going to be 1, and the lower limit it's going to be a half, right? Right. So yeah, right. So right. So what you see is that the terms are like these terms are 1 minus 1 over 2 to the n, right? This is 1 minus 1 over 2 squared. This is 1 minus 1 over 2 cubed, and so on and so forth. Right. So yeah. What you're saying, you said look at the even term. I'm saying the odd terms. Odd terms are all going to be like 1 minus 2 to the n. Right. And the even terms are going to be, half of that. Right. So you got terms that look like 1 minus 1 over 2 to the n, and you also have terms that look like 1 minus 1 over 2 to the n over 2. In other words, 1/2 minus 1 over 2 to the n plus 1. Right. So that's what those terms look like, right? And so, just sort of, you see that those guys, the upper limit is going to be 1. The lim sup is going to be 1, and the lim inf, right? You've got two sequences, one of which converges here and one of which converges here. So you've got the lim sup and the lim inf. Yeah. Which is what you were going to tell me, right?
Yeah.
Yeah.
But I wrote it, I kind of wrote the generic form of the even and odd terms a little differently. I got kind of to the same place, but I wrote it. But, okay, that helps.
How did you write it? Did you write it? Did you actually sum these things, or so you wrote this as maybe like 3/4 or something, or?
Well, I wrote out like numerically the first 9 terms to get an idea, but then I defined the sequence of odd terms where a1 is 0 and then an plus 1 is an over 2 plus 1/2. And it gives the same thing, but...
Okay. So you said, well, the odd... Say what you said again? What did you just say?
For the odd terms,
so A1
is 0, and then an plus 1 is an plus 1 divided by 2.
Is the previous odd term plus 1 divided by 2, right? Is the previous odd term, is that right? Is the previous odd term plus 1 divided by 2? Yeah, that's right. That's right, yeah.
So I guess I just wanted to, like, in proving this rigorously,
Yeah.
but then I just have to use that sequence of A's and then show that 1 is, it goes to 1. that's its limit?
Yeah,
Okay.
right. Yeah, because I mean, the point here is that I think, so how would you show it, right? You want to show that, suppose you have this information and you want to show that the lim sup is actually 1, right? The point I think you want to say is that, well, look, if you look at these values, there's only 2 limit points here, right? 1 and 1/2, right? Everything else is not a limit point, right? Because to be a limit point, you have to have infinitely many members of your set, within every epsilon neighborhood, right? And none of these other points are going to satisfy that, right? So only one. The only candidates for limits are 1 and 1/2, right? So the only limit points are 1 and 1/2, and you know that these are subsequential limits because the even guys, converge to whichever. The even guys converge to this, and the odd guys converge to this. Yes. Right. So you know that these actually are subsequential limits, and then the larger of them is by definition the lim sup. The smaller of them is by definition the limit. Yeah. Okay. Yeah. Anybody want to hear? Julia, did you come up with anything? Should I stop asking you?
Let me look at it again.
Okay. Yeah, take your time. You have something else, Sam? You look like you have something else.
I do.
Yes.
It's just another homework problem
Okay.
that stumped me was
Yeah.
chapter 3, number 5,
Okay.
where we're proving that the lim sup of the sum of sequences is less than or equal to the lim sups of the sequences.
Okay. Okay. So we have 2 sequences. And we want to show that the lim sup of the sum is less than or equal to the lim sup of those guys. Okay. Okay. So I'm not sure. Let's think. So let's think. So like lim sup of the A's. Let's call this thing alpha. Let's call this thing beta. Okay. So lim sup remember means that we have this sort of half limit idea, right? That given any epsilon, we can find a time past which everybody lies in here. Okay. Right. And here's beta. we can find a time past which everybody lies in here. Okay. So, right. So, putting those together, we know that there exists a time past which everybody, like all the A sub n plus B sub n are greater than or equal to alpha plus beta minus epsilon, and yet less than or equal to alpha plus beta. Right. Right. So I'm using the characterization of the limb soup. Right. I think that's kind of the easiest way to understand the limb soup as this half limit. Okay. So right, we know that given any epsilon, there's a time past which all the terms lie, all alpha, all A sub n are between alpha minus epsilon over 2 and all B sub n lie between beta minus epsilon over 2 beta, and thus you get this sort of thing, right? Right, but that basically gives it to you, right?
Mm-hmm.
Right, because then, then any subsequence of the sums, right, eventually is going to be trapped between those two terms, right? And so you see that when you take the limb soup of these guys, well, it's got to be less than or equal to this thing, right? Which is what we want. So that's in the case where these are finite, and probably the infinite case is something similar. Right? The way you want to think about it is sort of like, well, look, the limb soup, right, is all subsequences of the A sub n are going to be convergent, any convergent subsequences are going to converge to something less than this. Right? Any convergent subsequences here are going to converge to something less than this. Right? So if you're taking sums of subsequences and looking for convergent, summed subsequences, then there's no way they can get bigger than the sum of these guys, right? Because independently, these guys are sort of like taking the maximum value. The maximum value of one sequence and the maximum value of another sequence, and then asking, could the maximum value of the sum exceed this maximum value? Well, no way, right? Because the maximum here, plus the maximum there is definitely going to be bigger than the maximum of the sum. Right? Like thinking about it in terms of the max of. If you have some sort of finite sequence, right, if you looked at the maximum of these guys, that's definitely smaller than the max over one sequence plus the max over the other sequence. Right? That's basically what's going on here. Yeah. But if we would rigorously use the characterization. Okay. Anything else?
I have something I want to talk about.
Oh yeah, great.
Can we go over the supermetric?
Supermetric, yeah, sure. So the important thing about soup norm metric is its equivalence with uniform convergence. So, right, uniform convergence, right? Uniform convergence, right, means that you have this. So, can make all f sub n, can make the f sub n get within any epsilon 2 of f. So this is kind of the graphical way of thinking about it, right? So you've got this f, and you know that, no matter what epsilon tube you choose, right? No matter what epsilon tube you choose, we can find a time past which everybody lies inside the epsilon tube, right? So rigorously, given any epsilon, there exists a time past which fnx minus f of x is smaller than epsilon at every single point. Right, so when you're talking about uniform convergence, it has to be on some set. Uniform convergence on some set. Right? So on your set, right? On your set, the points don't differ by more than epsilon. Okay. Now soup norm is just you take the size of the function is defined to be the supremum of its values. Okay, the supremum of its values. So right. So you take the greatest value, the greatest of the absolute values of your function over the whole set. Okay, and then you define a metric by saying, well, the distance between two functions we're going to define as the soup norm of the difference. In other words, you take the supremum of the absolute values of the differences over the set. Okay, but f minus g in soup norm metric being smaller than epsilon means that the supremum of the difference over the whole set is smaller than epsilon, right? Which just means that f of x minus g of x is smaller than epsilon for all x in E. This is not quite right, but it's so this is, it's a little bit not quite right, but it's basically true. Okay. The reason is that going backwards, right? If this is true, then this would actually be less than equal to E. So, but the thing is that if you can make this thing's anyway, it's sort of close enough. Okay. Okay, but look at this. This is the same thing as this. right? Right. For the soup norm difference to be smaller than epsilon, definitely means that the difference between the functions is smaller than epsilon. But that means that G lives in F's epsilon cube. Or vice versa, right? F lives in G's epsilon tube. Right. So to say that for these guys to converge, to converge uniformly to F, these guys converge uniformly to F is the same thing as saying that the soup norm that this thing goes to 0. Right? Because we can find a time past which everybody here lives in the epsilon tube of this guy, right? But that's the same thing as saying that we can find a time past which, let me write this out. Fn converges to F uniformly means that, right, for all epsilon greater than 0, there's just a time past which this thing is smaller than epsilon for all x and e. But that's the same thing as saying that for all epsilon greater than 0, there's just a time past which this thing is smaller than epsilon. Right? But that's the same thing as saying that the limit of the differences is 0. Right? That's the definition. Right? Just like this is the definition here. For these guys to converge to F uniformly is the same thing as saying that the Fn converge to F in the soup norm metric. So, this idea of convergence changes into an idea of just points converging in some metric space. Did you get that, Julia? So, like,
yes.
Converging, this thing of convergence, which didn't look like, points at the beginning. Actually, all it is that you have some metric space, right? The continuous bounded functions on E, and you have a bunch of points in there that are converging somewhere. So it becomes, it changes the thing from chapter 7 back to chapter 3, basically. Anybody? Next question.
Could we also go over the Cauchy product of two series?
Cauchy product. Oh, okay. Okay. So this was this business of, right, you have one sequence, and you have another sequence, right? And you're trying to find, I'm sorry, what am I saying? You have one series, and you have another series. Right? And you have another, right? So you've got these two series, right? And you're trying to find some third series that, you want to find some third series that converges to the product. Okay, you'd like to have something like that. And so Cauchy's idea is that, well, you know, if these guys are finite sums, if these guys were finite sums, then right, if you had, you know, like A1 plus A2 plus A3 plus AN, and you multiplied it by B1 plus B2 plus Bn, well, what you would get is A1 B1 plus, you know, A1 B2 plus AN, A1 Bn. You get A2 B1 plus A2 B2 plus A2 Bn, etc., all the way down to AN B1 plus AN Bn. Right. I probably wrote this wrong. I should probably have written it like this. A1 plus A2 plus AN B1 plus Bn. Right. Just by distributive property, right, you take A1 times everybody here, plus A2 times everybody here, etc., etc. Okay. And so Cauchy's idea, the Cauchy product, is to find Ci to be the sum along the diagonal. Right? So Ck is going to be the sum as of ai times b n minus I, k minus I, as I ranges from 1 to k. Okay, so, right, C1 is just going to be do I have this? I've got this sort of written wrong. K minus I. We should add up to K minus I plus 1, maybe? I probably should have done this from 0 to n. Yeah, let me do this from 0 to n, sorry. So pretend we start from 0. Okay. So A0 is A1's. This starts from B0, B1. And B0, and yeah. Okay, okay. I think that works now. Right, so C0, and you sum from 0 to k. So C0, right, is just going to be C0 is just going to be you know, A0, B0. Right? Because you're going to sum from 0 to 0, you know, AI be 0 minus I, right? So it's going to be A0, B0, right? C1 is going to be A0, B1 plus A1, B0, right? These terms are going to add up to K, add up to 1, right? So these guys add up to 1, 0 plus 1, 1 plus 0. C2 is going to be A0, B2 plus A1, B1 plus A2, B0, and so on and so forth. Okay, so you get all you know, all possible sums that add up to 2, right? You get all terms that correspond to those guys, right? And so those give you, this thing. So, right. So yeah. So Cauchy is basically saying, let's pretend that we have this infinite product, you know, and we're going to, you know, if we want to think about, you know, the product of these two series, let's pretend that we would multiply them just as we would for just as we would in elementary school, right? We would get this infinite matrix, and we're going to sum it along the diagonals. Right? We'll call this guy C0, C1, C2, and so on and so forth. Okay, right? And so it's Merton's theorem that says that this thing, right? As long as what was the condition? Do you guys remember the condition? As long as one of them, you know, as long as this thing converges, right? As long as the C sub k converges to something, it's actually going to converge to the product of these things. Just a second. That's not Merton's theorem. That's Abel's theorem. Yeah, Merton's theorem is that as long as one of them converges absolutely, as long as one guy converges absolutely, then the Cauchy product will converge to the product.
I have a question about.
Sorry, is that enough, Julia?
Yeah.
Does that sort of answer your question of what this is? Or? Yeah. Unless Julia did.
Okay. Just kind of going over again why uniform convergence preserves continuity.
Oh, okay, sure. So, so let's see. So suppose you've got these guys that converge uniformly, okay? And suppose that these guys are all continuous, right? So the claim is that f is still continuous. Okay. So you think, well, you know, I mean, the point is basically that, look, you know, we can make these guys as close to f as we desire, right? So, you know, basically we can make f as close to a continuous function as we desire. And so f is going to be continuous, right? Right? Because look, I mean, what does continuity mean? Continuity means that at every point, you know, you can find a neighborhood in which it doesn't jump too much, right? So like you say, look, I don't want you to jump that much, and I can find a neighborhood in which you don't jump that much, right? Well, if I can do that for f sub n, and I can make f as close as I want to f sub n, then f is going to be continuous too, right? So that's the intuition, right? You say, well, look, here's f, here's some point x, right? So we want to show that f is continuous at x, i.e., you know, given any epsilon, there exists a delta such that if the distance between x and y is smaller than delta, then the distance between f of x and f of y should be smaller than epsilon. Right? So you're trying to find, you know, somebody gives you an epsilon and says, find me a neighborhood in which you don't jump that much. Okay, find me a neighborhood in which you don't differ from this value by more than that, by more than epsilon. Okay. And you say, well, look, you know, I can get the f sub n's, who I know are continuous, to be super close to f, right? So choose n such that, you know, the distance between f sub n and f is smaller than epsilon over 3, say, right? So I know that there's somebody close by, right? That's my epsilon. I know that there's somebody close by, right? Right? I know that there's somebody close by, f sub n. And its difference from f over the whole space, you know, is always smaller than epsilon over 3. Okay, and I know that that guy is continuous. Right? I shouldn't make it go through the same point. Right? I know that that guy is continuous. Right? We know there's a delta for f sub n. Right? We know there's a delta for f sub n, right? In which f sub n values don't differ from y by more than epsilon over 3. Right? So f sub n, we know we can control it so that, you know, there's a neighborhood for that guy in which the values don't differ from its value at fnx by more than epsilon over 3. Okay, and then you just use the same old, like, you know, slide in the whatever. So then, right, if we're looking at f of x and f of y, well, we know that that is smaller than the distance of f of x to f of n, plus the distance of f of n to f of y, fn of y, plus the distance from fny to f of x. And each of those things is smaller than epsilon over 3. Yeah, so it's a sort of standard argument. The uniform convergence is just used to get one guy who is close, and then you say, well, that guy's continuous, so, you know, we can do it. So yeah, so you know, Rudin of course proves things in a more general manner, but that was for that reason. Remember, we needed the more general theorem to prove the differentiability theorem. But it could be done it could have been done pretty simply this way.
Okay.
Okay, that's it. So you guys see you on Thursday, right?
Mhm.
Right.
What time is it again?
Oh, I don't remember.